Earlier we mentioned that aerogels are remarkable and that they're an excellent insulator for heat. And that's shown in this figure here, where we can see that we have a Bunsen burner flame, and with this small slab of aerogel, the rose is protected from damage. The question is, how do we make aerogels? If we look at a gel is made up of a network solid. So we have this complicated network of solid, and then there's solvent in here. And that would be just a gel. What happens when we dry out a gel? When we dry out a gel, it tends to crack. Why is that? Well, if we imagine drying out a gel, let's just look at two pieces of solid. So we're looking at a pour where you've got liquid, you've got solid, liquid between it. And as it starts to dry out, we form a meniscus. And if we look at, for instance, a gel made from silica, silica is going to be hygroscopic, or rather hydrophilic, and so it forms this type of meniscus. And we know from the Laplace equation that means the pressure inside is going to be less than the pressure out here. So if we think about this solid piece of silica, if the pressure is less in here than in here, that's going to tend to produce a force in this dimension on both pieces of solid. Okay, since the pressure inside here is less. And so that's going to tend to crack the silica. And this is why things crack when they dry out. So that's why normally if we just dry out a gel, gels tend to go to zero gels. And a zero gel is just a cracked, shrunken gel. It looks kind of like dried mud. So how do we make this, where the original shape is retained and it's not cracked at all? I'll show you that on the next slide. So let's imagine for a second that the solvent's water. So we've got gas, liquid, and solid over here. Okay, so normally when you dry things out, you're starting off with liquid and you raise the temperature, or equivalently you can lower the pressure, and the liquid boils in either case. Okay, boils or vaporizes. In either case, whenever we go and have liquid-gas coexistence, we're always going to have a meniscus. And if the meniscus is curved, we're going to have Laplace pressure effects and hence cracking. So the way around this is to actually take the liquid and heat it and increase the pressure, and then raise the temperature at that higher pressure. And then lower the pressure. And notice what we've done. We've gone around the critical point. And so we know up here we don't have liquid or gas. There's no distinguishing between them. We just say we have supercritical fluid. So by taking this supercritical path, we never have coexisting liquid and gas, and hence we never have a meniscus. And without a meniscus, we can't have Laplace pressure effects. And this is how we can get rid of all the solvent in a sol and go to an aerogel, where we've replaced the liquid with the gas, but by taking this indirect path, there never was a phase boundary, and so there wasn't any cracking.